A warm good evening to everybody. Professor Pantelis is here. Our president is also here. We are at SGAT Bhubaneswar with my colleagues, Mr. Mohanto and Mr. Jair Patnaik, along with event manager Sri Devasis Parida. We are also joined here, and number of attendees also have joined. A warm welcome once again to everybody in the invited lecture series 2021, and this is the first lecture of the series to be delivered by Professor Pantelis Soupios, and we know the topic is engineering geophysics in urban planning and environment. We are very happy to observe that after a gap of more than 1 year, we have been able to revive this lecture series under the guidance and inspiration of our President, Dr. Omkarnath Mohanty. And this is likely to continue, and every 2 months we are going to have such talks. But anyway, this is the first one, and we welcome Professor Pantelis of Department of Geosciences, King Fahad, University of Petroleum and Minerals, Saudi Arabia. A warm welcome to you, sir. We also welcome our President, Dr. Omkarnath Mohanty, and all my seniors, my colleagues, and there are few attendees. There may be some students also. And with this, may I request our President to kindly speak a few words before we start on the proceedings. Dr. Omkarnath Mohanty, please.
Good evening to Professor Pantelis Soupios. We say namaskar as we said yesterday. And to everyone else also very good evening. So on behalf of the Society of Geoscientists and Allied Technologists, I have great pleasure in inviting you all to this evening's lecture by Professor Soupios, who is a professor of near surface geophysics in the FUPM, and he's also the program leader in geophysics and CIPR CPG, and he's going to speak to us on the engineering geophysics and urban development and environment. And the Society of Geoscientists and Allied Technologists is actually a pioneer body as far as Odisha, the province of Odisha is concerned. Nay, as a matter of fact, the entire nation is concerned, because this is one of the largest with more than 800 members and has been working for over 40 years now, and with a very wide spectrum of activities. And one of the things that we intend to do every time is to provide a bridge between several disciplines which are connected with geology, physics, mineral engineering, as well as the metallurgical activities. And this forum is primarily meant for that. And I have great pleasure in a way, inaugurating this bi-monthly webinar, as our secretary has rightly said. And hopefully we will be able to continue with international experts. And as far as today's lecture is concerned, Professor Soupios, I want to tell you that we are looking forward to your lecture with great amount of excitement and interest, essentially because of the fact that in you we see 2 or 3 very important things. Number one, of course, you are a bridge between India and not one but 2 countries. One is, of course, the ancient countries of Greece and India. And I know that somebody who comes from Crete would like to be known as a person from Crete rather than only from Greece, because you are proud of your own island and such a beautiful place that Crete is. Well, I had seen that. So which is why, so that's one bridge. And the other one is, for the past 3 years, you have made South Arabia as your home. So our second bridge with your adopted home. And the third bridge, of course, is with the institute, with the discipline which you represent, namely primarily geophysics, geology, and mineral engineering and petroleum engineering. So these 3 bridges we are creating, or we have created. And as far as India is concerned, The petroleum as such is of great importance to this country because more than 82% of our petroleum requirement in India we import. And that actually is greatly taxing as far as the India's entire economy is concerned. So, and added to that, the pandemic that we are talking about is the pandemic, and the COVID-19 has been a great strain on this country as it has been with the rest of the world. But on India in particular, because of the fact that our petroleum production as such was low, less than 1% of the whole world, and it has gone down even further. And so we, through your lecture, and we are looking forward to yet another bridge, namely, can we have an interaction with you so that we would add to our petroleum production in future, exploration in that area in future. Whereas your lecture on the urban development and environment, along with and the connection with geophysics, should be of great interest. And I have great pleasure also in telling all our colleagues that we have with us a number of students from the various universities. As far as India is concerned, Professor Soupios, there are a number of places where petroleum engineering is taught. That's correct. But we have two full-fledged universities. One of them, both of them are private universities. One of them is the University of Petroleum and Energy Studies, which is in Dehradun, not far from Delhi, and in the north of India that yesterday we are talking about. And this has been operating for the past 18 years, to be precise, since 2003. And the other one has been set up by Ambani's, by the Reliance Group, and that is the famous Pandit Deen Dayal Petroleum University, which for the past 2 months, only 2 months back, it has been renamed as the Pandit Deen Dayal Petroleum University, has been changed to the Deen Dayal Energy University. So these two are the full-fledged universities. In addition to that, as many as 4 IITs also have introduced petroleum engineering. That includes the IIT in Bombay, the IIT in Madras, which is down south in Chennai, IIT in Guwahati, which is the northeastern state, and IIT in Dhanbad. In addition to that, a large number of other institutes. So hopefully some of the students who are present here and the university teachers who are present here, they would also look forward to your university and through you with other universities in Saudi Arabia in establishing these contacts. With these words, I once again welcome you in our midst, although in a virtual manner. Hopefully very soon we would also be meeting in physical manner also, and we would have the pleasure of welcoming you in our midst in India. Thank you once again and welcome to this lecture.
Thank you, Dr. Mati. Now we have a learned speaker, Professor Pantelis, but we must know what is his depth of his knowledge and where all he has worked. So may I request Dr. Sri Girija Prasad Mahapatra, our Vice President, to kindly introduce the speaker to the audience. Sri Girija Prasad Mahapatra, please.
Thank you, Panigre sir. I think, is it audible, sir?
Yes, you are audible.
Yeah, you are quite audible.
Good evening to Dr. Pantelis and as well as our President, Dr. Mohanty, and all my panelists who are there and other students. I am having the honor that Pantelis Soupios is present here. He is a learned man of both the caliber, having a geophysics and geologist. So now let me have some of his briefing up about his whatever the career he had. Dr. Pantelis Soupios is a professor of near surface geophysics at the Department of Geoscience, King Fahad, University of Petroleum and Mineral Kingdom of Saudi Arabia. Pantelis Soupios obtained his BSc in geology from Aristotle University of Thessaloniki, Greece, and his MSc and PhD in applied geophysics. So both he is having geology as well as the geophysics. He started his career in the Laboratory of Geophysics and Seismology of Aristotle University in Greece. He worked as a young researcher in the Uppsala University of Sweden. and Denmark Technical University also till 1998 as a senior researcher at the Department of Applied and Engineering Geology, University of Basilicate till 2011, and is visiting professor at Ankara University, Turkey 2009 onwards. His expertise and research focus are on the electromagnetic, electric, seismic methods in geophysics and joint inversion interpretation of geophysical data sets with application to environmental, water resources, and engineering purposes. Dr. Pantelis has established a strong international research network for collaboration and has authored and co-authored 2 books, 11 chapters in a book, 54 articles published in a scientific journal, and 80 conferences papers covering the broader area of applied geophysics, Soupios Index 18 and 1171 citations. In addition, he has 6 years of industrial experience in engineering geophysics. His expertise is on the application of several geophysical methods for environmental hydrogeological engineering application and geohazard studies from 2002 to 2018. He is currently a professor of near surface geophysics at the Department of Geosciences, KFAU Kingdom, Saudi Arabia. And just a little bit, I think some more introduction I will give it. His expertise is in the field of environmental and engineering geophysics, applied hydrogeology and hydrogeophysics, applied geology, and agrogeophysics. It is a separate topic. I think we are sure he will be telling something about that one. And archaeogeophysics at selected archaeological areas using various geophysical methods. Advanced geophysical, geological, geochemical method for waste disposal sites in characterization. And groundwater and soil monitoring also, his specialization is there. And this is a brief about Dr. Pantelis. I think it will be a pleasure to hear from him the topic which we have selected, and we are honored by his presence and his deliberation on the virtual mode. Thank you very much, sir. We will be waiting for you. Deliberation. Dr. Panigre, please.
Thank you so much. Shall I start? Can you hear me?
Yes, sir.
Yeah,
I think
please.
please
Okay.
go ahead. Yes,
Great. Okay. So I would like to thank you all for, first of all, for the invitation. I would like to thank also one of your members, Tim Gupta, the one professor who has some collaboration so far with India. And of course, I have also very good collaboration with, I had 2 students from India that I'm really proud of these guys. It's Mohammed Sarouk, who is now working in BP and in UK, and also Payal Rani. She's assistant professor at university in India, and we're very good collaborators. Anyway, so it's the idea to give you an overview about the application of engineering geophysics for the urban development and environment. I'm going to skip these slides because this is just present myself briefly, but the secretary already do that. So it's, first of all, I will start with the outline. I'm going to present you the geophysics, and I am going to give you a short introduction about the geophysics. Then I'm going to move to the urban geophysics, and I'm going to show you different parts of urban geophysics, like the urban, where this can be applied for the urban expansion, the natural resources exploration, the environmental monitoring, and the climate changes. I will present in different scales, which is very important to understand that actual geophysics is not only for the field, can be applied in different scales, in meso scales, but also in the lab in micro scale. Then, as requested, I'm going to give you an overview about the current situation of the mineral exploration in Saudi, in the kingdom. And I'm going to close this presentation as the last part of the presentation, presenting our college, the college CPG is the College of Petroleum Engineering and Geosciences of KUPM, the university called King Fahd University of Petroleum and Minerals. So what is geophysics? There is a very good definition by Professor Serif in SCG. So geophysics, as you can see here with the highlights, is the characterization of the subsurface. I'm talking about geology, geological structure, which means tectonics, groundwater, contamination, human artifacts, in all directions, in all different dimensions, lateral, vertical dimensions. And we are trying all the time to reconstruct some physical properties of the subsurface. So this is the idea. And why? Because we need some benefits from this. So we need to explore some economic materials, to define and find the natural resource like the groundwater, the oil and gas, and so on. There is another definition, like geophysics is the non-invasive investigation. This is really important because geophysics belongs to the NDT methods, non-destructive methods. And this is very important in case that we are going to work in archaeological sites and so on. Can be applied in different environments, in the water, so waterborne measurements, airborne measurements, land measurements, bore geophysics within the boreholes. And the idea is that we can apply geophysics from the top few meters, let's say from 0 till the maximum depth of 5, 6, 10 kilometers. You can see here on the bottom some photos, so you can apply geophysics at different weather conditions, in desert environment, in semi-arid, next to the water, water measurements under the rain, within the waste, during the night. So there is no limitation on applying geophysics. I tried before, because I prepared today the presentation, I was trying to find something in order to introduce the urban development environment. So I minimize the part environmental geophysics in, which is part of the title, and I just, let's say, maximize the urban development environment. So I found this editorial from 2007, says that economic development, this is the highlight part, especially in the Asian Pacific region, force the people to have some rapid urban expansion, creating shortages of energy, resources, degradation of the environment, and changes the climate patterns, which means that now we are moving, we have some urbanization. The most of the people, it says in the second part of the highlight, says that for 50 years, less than 50 years ago, the 3% of the world population was just living outside the countries. Now, more than 50% living within the city centers, which is the 1% of the Earth's surfaces. So you can understand that the stress is really high. So we are facing several problems. The first one is the rapid urban expansion. The second one is the shortages of energy and resources. The third one is degradation of the environment. The last one is the changes because of the previous one to the climate patterns. Okay, so you can understand that I'm going to focus on these parts, and that's why on the overview I told you that I'm going to discuss about urban geophysics, in urban expansion, in the energy and resources, in the degradation and environmental monitoring and the climate change. And you know, someone asked, okay, Pantelis, you are part of the problem for sure. You are living in the city centers. You contaminate the planet. You are part of the, but you should at the same time some actions in order to decontaminate, in order to improve the life. Okay, so I would prefer, let's say, to not be only part of the problem, but to be also part of the solution. Okay, and for that reason, we are using urban geophysics. So I'm going to show you different examples about the urban geophysics. I will start with the urban expansion geophysics. This is Greece. This is on the south part is Africa. On the east part is Turkey. North part is and Albania and Bulgaria. So I was born in northern Greece, but I spent about 15 years in Crete. Crete is the south part of Europe. Very beautiful place. This is one very zoom of the Chania city. Chania city is the western part of Crete. And here you can see the base, the bus station in the city center. So if someone wants to do any kind of development, any kind of investment, like the guy who is the owner of this hotel, so there is one owner of this land, and these two buildings is one hotel. So in 2009, this guy, the owner of the hotel, asked me, Pantelis, I mean, can you apply any type of measurement, any type of methods in order to survey the subsurface, to make a mapping of the subsurface and start thinking how I can invest money and build a new hotel. This is part of the development, okay? So I asked why, where is the problem? The problem was that very, very close to this site, they found some archaeology relief. They found some archaeological findings. And in this case, the archaeology here is very powerful. So if they find something, they suddenly stop any construction. And after that, they pay, let's say, the 1/10 of the cost of the cost of the land. And then they get the Ministry of Culture, get this land under their supervision. So they were afraid that probably if they start digging and start building something, they find something this area was about 50 meters far. I go back, so it was here. If you can see the mouse pointer, it was really in the next block. So it was less than 50 meters from the area is here, the parking area of this land, and they found this geological site here. So we did several surveys. We applied electrical and electromagnetic methods. We did a full 3D model of geoelectrical measurements. So you can see that after 3D modeling, we defined some circular structures on the left side, okay? And that was defined based on this is the steady area. It was here where the hammer is. And this is the depth slice at the depth of 1.1 meter. And of course, I had to go back and try to reconstruct the history. Because if it was, let's say, something similar to this circular structure, like a shaft, an ancient shaft, and I have to mention that the age of this structure is 1,000 years before Christ. So it's 1,000 BC, okay? So we found this circular structure. So I had to make an interpretation, and this is the difficult part, because the main characteristic of the geophysical methods is the non-uniqueness of the solution, which means that you can get through the numbers, through the models, several solutions, which is the right one, which is the correct one, what is really makes sense in the geological point of view. And that's why I'm feeling really lucky that I'm geologist and geophysicist, because very often I can combine my knowledge or I can constrain the uncertainty of geophysics based on the geological evidence. So I tried to find one picture. Let's see, here you can see the different balconies from the different stories. And this is a picture from 1951, after a few months after the Second World War in Europe. Okay, so you can see the bus station, but we're talking back 60 years. Okay, and there were this area, it was the hotel here. You can see on the left side the hotel exactly from the same location. This was the reason that I found this photo, and then I went in the same story and I took the same photo from the same angle in order to show what was this anomaly. So this circular anomaly is this oil tank. So this factory was an oil refinery tank. They were producing olive oil, and they were just storing all the oil or the water from the processing inside this tank. So it was the base of the tank. So after that, we gave the green line and they start building the area. But I would like also, so this was a very local case. I would like to scale it up and show you an application of geophysics for urban expansion and urban design for future building, and so on in city scale, okay? So we decided to submit one proposal about, the name was geocharacterization. It was under the European Union and the Safe Cities call. It was about the natural hazard and especially the seismic risk. So in different areas, in different big cities, so this is Crete, okay, in the southern part of Greece, in different cities, we applied different geophysical methods. So you have always keep in mind as a student, as a young researcher, as a senior researcher, that geophysics and geology is, let's say, one science. That's why we belong to the geosciences. So we started from the basic geological mapping. We collect all the preliminary information. We collected the geological map. So this is the geological map of the city. And then we did some geological mapping. We went to the field. We collect some information about the different formations, the different fracture zones, some discontinuities that we can find, some unconformities. Okay. So after that, we revised the geological map. So you can the revised geological map. We found some features, some tectonic features like this, but you can see that is mapped like dust line because we didn't have any real evidence to prove that there is a fault unless we apply some geophysical measurements. Okay. So we construct these cross sections for the steady area. I'm talking about Chania city. And then we did one borehole. Okay, so we had the boreholes, we did some SPTs. SPTs is a standard penetration test, and is important in order to characterize empirically the change of vertical of the VS, so the VS waves velocity with the different depths. Okay, so you can see here the logs, you can see here the recovery, you can see also the SPTs at different depths. Then we revised again the geological map, and we include some more information based not on the surface mapping, but based also on the information we got from the logs for the different horizons till the maximum depth of 50 meters. That was the maximum depth of penetration for this borehole. And then we revised the geological section. So the next step is to get this sample and to go to the lab. So it's very important part to apply the soil and rock mechanics test in the lab. We applied unaxial, axial tests in the different samples. We did some VS measurements or VP measurements using the better elements. And most important, we were able, for the different places, at different depths, so sorry for Greek, but I found this report today. So this is the borehole, this is the depth in meter, this is the VS, the velocity of the S waves in meter per second, the peak waves, the Poisson ratio, the elastic modulus, and the Young modulus. So you can see that we were able at different depths. If I would like to focus on Chania, okay, so at the depth of 6, we have this velocity, 21, this velocity, different in VP, different in Poisson. So the next step is doing geophysics. So the geophysical method that we applied was, we have one seismic station here. Actually, we have one accelerometric broadband seismometer here. So we're measuring acceleration. And then we applied very close to this, the borehole. So this is the borehole that I showed you before. And we collect the data and we did the lab experiments. This is the seismic line within the urban environment. This is the geoelectrical line. And the dots here is different seismometers, broadband seismometers at different diameters that can provide in a very high accuracy the VS model till the maximum depth, depending the ratio, the maximum depth of 500, 600 meters. Okay. So this is the VS model, this is the DC model, the resistivity, this is the VP, I mean the velocity of the primary waves, this is the resistivity. So we're able to find in 2D how the formation, how the geoelectrical, the conductivity, or the velocity changing in depth, but also laterally. Then by applying these different span methods with the seismometer, the broad seismometer, we're able to find the VS model till the maximum depth of 500 meters. And of course, to be able to apply passive and active methods, seismic within the same line, along the same line, to get the VS profile by applying the refraction microtremors, the REMI. Now, why is this important for the designing or the plan for a future expansion? Because based on the geological maps, we have the different stations in the different cities. This is the presentation. This is actually the characterization of the different formation based on the geological maps. The IGME is the Greek geological maps, the Greek Geological and Mineral Exploration Survey, the agency. So this is the governmental association. So this is the different types of soil. So this is ST means soil type. Then we applied the high resolution mapping during with some fieldwork together. So you can see for Chania, from category C, we moved based on the geological mapping and the high resolution mapping, we moved to category A. After applying the borehole data, we moved to category E. And after applying the geophysical investigation, we moved to the category B. What are all these categories about? So we were able, this is from Refimo and another we were able to get the VS model for the area, for the steady area, based on the geophysics, based on the laboratory measurements. BS is Bender elements, the VS based on SPT, and of course, the SPT values with depth. So why is it important? Because in order to design a structure, you need to follow a Eurocode. So in Europe, we have the Eurocode 8, which is very strict because of the many earthquakes that we have. So you can see this is the different ground types or the soil types that I showed you before. And the way that they characterize and they discretize, they classify these different is the VS30. VS30 means the velocity till the maximum depth of 30 meters. To tell you the truth, this started from US, and US they have VS30 and they mean 30 feet. Okay, so it's 1/3 of the 30 meters, so it's 10 meters, but in Europe, we decided to follow the 30 meters, okay? So you can see that they have different velocity variation for VS in order to go from one type to the second type. And again, why this is important? Because it's not very clear. If you know that the different types, soil or rock types, then if you get the seismic motion, you can estimate very easily the soil amplification. You can estimate how the structure behave in case the wave is propagate. So you can estimate the soil structure interaction that is very known in the civil engineers. They call it SSI. So the idea was to be able to avoid damages, to be able to renew the anti-seismic code based on the local geological and geotectonic characteristics and revise the anti-seismic code. Why? In order to increase the safety in our cities. Okay, so this is just an example. You can see, for example, close to the rock, we have almost zero amplification. If you are close to the epicenter was here, this earthquake, which is really a very known example. Inside the valley, we have some sentiments with different variability in velocities. You can get a very high amplification, very high amplitude. So this is one example about the design, the related use, and the defined, the calculated response. You can see, for example, for Chania, the spectrum based on Eurocode 8, which is the newest in Europe, it was within our measurement. So the blue lines, the green, the red lines are our examples, our estimations in two different directions, in horizontal and in vertical. Horizontal, north, south, east, west, and of course the perpendicular, the horizontal with depth. But you can see, for example, that in Heraklion, the inhomogeneity was so complex, so the near surface characteristics were really so complex that affect the behavior of the soil was completely different than the expected. So, for example, all the buildings, they are very vulnerable, so they are in high risk in case of an earthquake. And this is the result of 4 days ago. This happened 4 days ago. One earthquake, 6.3 in Kozani, is in Larissa, I'm sorry, in the central part of Greece. So in this area, they built this school. So this is a school. We were lucky because it was, because of pandemic, the students, they are doing all the courses virtually, which means that they were not inside the building. You can see that the building is almost collapsed. If you go inside, I have some photos from inside. I don't want to spend your time. So it's very important to know the local soil condition, and this is part of the geophysical urbanization. Now I'm moving to the shortages of energy and resources, and I'm going to focus on the groundwater because the people, they're expanding, they're going to, let's say, go to the city center, but the city center is not enough. So the city is expanding and we need more resources. And the most important resource for our development, any type of development, is the groundwater. So I'm going to show you some results from one area from the central part of Crete. This is Europotamos. Very complex area. And why it was very complex? You can see here boreholes and springs. So this is the springs. The one is sweet water. The other is saline water. So you have next to the other, this is the sweet water spring. This is a saline water spring. Okay. The distance between the two boreholes is 100 meters. So you can see that there are many, you assume that there are some homogeneities that change the quality of the water. Even the source, the recharge is coming from the same source. Okay, So you have also some boreholes. You can see that all the red triangles are irrigation well, so it's not drinkable, and the blue are drinkable. So you can see that this is bad quality, this is good quality. So how is possible? And there is an empty space here in between where we don't have data. Why we don't have data? So when I visit the municipality, I told them, guys, you need to just give me more information. Why you don't have borehole there? And they told me we have many boreholes, but they are all abandoned because the salinity was really high, even higher than the water that we used for irrigation. Okay, so here there are boreholes, many boreholes, more than 30 boreholes, but they are just they just destroyed them because the salinity was really high. So the idea was to apply geophysical methods, but we had to collaborate with geologists, and the old-fashioned geologists, they don't believe geophysics. This is something that we know. I also know. I'm not young, I'm not old, so I'm in between, and I'm trying all the time to bridge the different disciplines and say, guys, we can work all together. To tell you the truth, I need the geologists in order to control the geophysical measurements. Okay, so this is what we did here. We got the boreholes. We had the TM measurement. The TM means that we have the resistivity on the x-axis, the resistivity change with depth till the maximum depth of 200 meters. This is a borehole, and we would like to validate or confirm the geophysical results. And you can see that in the area that we have change in formation, we have change also in resistivity with depth. So I was, let's say, really convinced that my data, first of all, is good. And of course, I was able to explain to the geologists that we are doing our work in the best way. Of course, they asked me, can you provide us, based on the different EM, the different 1D resistivity models, can you provide a pseudo 2D section, geophysical section, and then overlay the geological section and show me that the geological formations fit well, are in agreement with the geophysical units. And this is what I did in the lower part. So you have many, many soundings. I just decided to have one cross section. So you can see with the bold black lines, the geological section with the different, so this is Planter-Calc Triassic, Neogenes, Quaternary formation. This is Triassic Cretaceous. So this is a different lithological units. And here with colors is the different resistivities. So you can see more or less that we were able to find here the hard rock, the compacted, unsaturated hard rock, and you can find here the formations, the karstified Planter-Calc, which was fully saturated with groundwater. Okay, so it was, for me, it was a great, let's say I was really happy because I saw them, guys, this is the geological and geophysical section at once. So we collect the data. This is the Europotamus area. And you can see, we always start from geology. You can see that this is the geological map. So I had to think why the quality in here, so here in the center, the quality was bad. So I start considering, is it something local like a gypsum, like a halite that changed the quality of the water? Do I have any saltwater intrusion from the sea? Because this is a coastline. But how is it possible to have a saltwater intrusion if here on the northern part I have phyllites and quartzites? Phyllites, we know from geology that is impermeable. Okay, so the only reason to have some saltwater intrusion, if this is the case, if this is a scenario, is to have some fracture zone. Let's see. So we collect the data. We collect more than 1,000 soundings in 350 different locations. And I'm going to show you the section AB. This is a geological section. This is the geoelectrical section in resistivity. This is the boreholes that we use in order to make the comparison and the validation. This is the seawater intrusion. So you can see that within the phyllites, we have seawater intrusion, and we have also some areas that the conductivity is very low, close to 1 omometer, which means that this is also saline water inside almost 2 kilometers inside the inland. Okay, so we collected all these 1D points and we created a 3D volume of geoelectrical data, and then we created depth slices. So this is the depth slice of from 0 to 20 meters. 20 to 50 meters. So you can see now, here is the surface geology. This is phyllites, quartzites. This is the sediments within the basin. This is the plattenkalk, the limestone with the highest resistivity. And suddenly you can see that after the depth of 20 to 50 meters, it seems that the resistivity is dropping down. And we have like a corridor here, we have some discontinuity. If I go deeper, 50 to 100 meters, the seawater intrusion is coming inland. And if I go even deeper, I mean 100 to 150, which is part of, you can see here, so here we have very low resistivity, we can go even lower resistivity. So we decided to use also geochemical because it's very important to get information and integrate different data or disciplines that they can correlate with geological. So we collected the different periods, different geochemicals. We created the different mapping of the quality. So this is the groundwater quality index. This is the groundwater quality map. You can see that based on the chemical parameters, it seems that here in between, the quality is the lowest. That is really in a very good agreement with the fracture zones that really bring all the seawater inland. So this was finally the conceptual model that we used. And after that, we suggested where will be the new boreholes in order, the new hydro wells in order to increase the production, the abstraction of the water. I will continue with the third part, which is the degradation of the environment. So we are talking about environmental geophysics, and I will focus in landfills, okay? So here is the one side. This is one of the most famous in Greece because till now we pay about 1,000 euro, so $1,000 per day because it's illegal. And not only illegal, is freely disposal. I mean, they don't control it. It's completely uncontrolled. So the municipality, the prefecture of Heraklion, requested from our laboratory to go there and do some measurements within the waste in order to be able to fully characterize the site. Because if they would like to sell the land, the price, even the island is very beautiful, it's very touristic. This area is very close to the coastline. You can see here that this is the area, and this is one of the most beautiful area in Crete, in the northern coast of Crete. So it is very crucial to define, characterize the subsurface and continue with the reclamation. So we did some, first of all, I did the geological mapping. So I went in, I collect all the data. So you can see that we have dolomites and limestones. We have some metamorphic basement, some schist. And I was really lucky because I've seen that the most of the waste disposal site was on the schist. And you can see here that it seems that it's impermeable. But at the same time, there are some areas like this one, it's phyllites and schist, but you can see a very beautiful fault, very beautiful for the geologists, very bad for me that I was sure that I would find some leakages of the waste into the deeper horizon, contaminating the groundwater level. So we collected many geophysical lines crossing the waste disposal sites. This is a different geophysical methods: seismic refraction, electromagnetic, very low frequency electromagnetic, DC, electrical receive tomography, and H/V seismic method. So this is the measurement, the instrument. So we can see that I was measuring just over the waste, different type of waste. I found some boreholes in order to be able to do the confirmation of the model and to have some measurements for comparison. And this is the final geophysical model. So you can see that we have the bottom. At that time, the thickness of the waste was more than 30 meters. We were able to find and classify the different horizons like organic waste, non-organic waste, and on the bottom, of course, we have the saturated organic waste. So all the fluids, all the leachates that they were going down following the gravity, and they were just constraining, if it's constraining, by the bedrock, okay? For example, here, we were not able to find, like here, the bedrock. So if we assume that we have a fracture zone, all these fluids, they are going deeper. But again, we are talking about shortage of natural resources. What if we are able to define, to estimate the landfill gases and produce energy from the biogas that's produced in the landfills. So we collected we built one closed static chamber, and we were measuring for every 30 minutes the released CO2 and methane. Okay, so this is the location of the static enclosure chambers. So this is the location along the lines, along line 2 and line 9. And then based on the different classification of the frequency of the resistivity, we're able to have the saturated organic waste, the organic waste, low organic waste, and non-organic waste. We were able to define the thickness of the organic waste. And based on the organic waste, we're able to define, with this empirical relation, the released landfill gases, okay, from the measurements of CO2 and CH4, the methane, in the different locations. So at the end, we were able to define the expected methane emission, to make the calibration with the measure, and of course, to estimate the power that we can produce based on these landfill gases. But this is some field experiment. Last December 2020, we had one master student from here, from Pakistan, that he would like to do some geophysical to combine environment. So this is master students in the environmental program of our department. And he wanted to apply to combine geochemical measurement with geophysical measurements. So the idea was to apply some laboratory measurements and estimate or monitor the decontamination of the groundwater. So the idea was, since, especially in Saudi Arabia, we have scarcity of water because we are in an arid area with less recharge, we don't get precipitation. At the same time, it's very precious, but in general, the water is contaminated because they don't follow the environmental issue, they don't follow the environmental regulations. And one of the contaminants, which is more known in the Asia, and also in the part of Middle East, is arsenic. We decided to use arsenic as the pollutant. Okay, so you can see here the area that especially the arsenic is a great problem, and for that reason we decided to experiment it using pollutant as the arsenic as a pollutant. So what was the idea? The idea was to get one laboratory column, to have some pure sand in our case we use the Ottawa sand, to mix with biochar. What is biochar? Biochar is one material that can produce by organic material. So it's a carbon-based organic material that produced by the pyrolysis of waste. So what is the idea? The idea is that we have waste. Waste from what? From the date palms, because this is really the third largest producer of dates with the world, and Soupios is Saudi Arabia. So we have tons of waste from the palm trees. Okay, so we took the trees, we took the leaves, we cut into small pieces, and we produced some biochar. So we had the biochar characterization, and the second part was to use the biochar as absorbent and the arsenic as the contaminant, and the SIP as the monitoring tool. So the biochar, you can get the waste, you can produce by pyrolysis the biochar, and this is very important because the biochar has very high sorption capacity, and it's very easy to regenerate it. It's very stable. Okay, so there are many, I'm not going to stay more in biochar because the most important for me part and for you is to show you the geophysical application. So this is the SIP setup and configuration, the analysis. This is the columns. So we inject current on the upper and the lower part. So this is the current electrodes. And on the side, we have the potential electrodes. We inject current, we measure the potential difference, we estimate the resistivity, and we would like to show if the biochar really absorb the arsenic, and if we are able, by measuring the resistivity change during the process with time, to find these changes. Okay, so this was, to tell you the truth, the first time that we applied here in Saudi. In Europe is the second time. The first time we applied in Greece in collaboration with one university in Germany. So first of all, the biochar produced was very good absorbent, because you can see the concentration after 30 minutes was reduced from 5.5 to 1. Okay, so this was a great achievement. But now what about the SIP? Is possible SIP to monitor these changes? And you can see that measuring the real conductivity and the imaginary conductivity within the column, we were able to find the changes with time after a few hours. So you can see the concentration here was high, and this is very low. So in between, you can see how the imaginary component of the resistivity measurement was really dropped down. Okay, so this is an evidence, this is some indicator that you can use SIP as as a monitoring tool. So someone can ask me, okay, Pantelis, how it's possible in this very, very small scale to apply geophysics and get changes inside the biochar? So I'm going to show you this SEM electronic microscope images in different zoom. So this is the biochar, and this is a biochar 500 degrees, and this is biochar produced with 80 degrees. You can see the structure is full of voids, it's empty. The structure is like a sponge and is waiting the contaminant to absorb. And you can see here, the biochar from 500 degrees, 500 degrees, before the absorption and after the absorption. You can see all this part are the arsenic. We did also some XRI and XRD in order to define this component. So what is SIP? SIP measure the changes within the structure of the nanomaterials. Okay, that's why we were able, and this was the idea why we decided to test it. I'm going now to close this part about the urban geophysics with certification and geophysics. This is just an idea. I didn't apply it. I submitted in Horizon. Horizon is the most competitive, it's Marie Curie project in Europe. It's very competitive. It's 4 million euros and is a single person. So I submitted as a person under my university, this CRC advanced proposal. So the title of this proposal in 2017 was Integrated Monitoring of Biological Soil Crust, they call it biocrust, using innovative environmental methods spanning multiple scales. And I was planning to do the application in the Southern European region. So the acronym was Trust in Biocrust. Biocrust is the name of this biological soil crust. So what is the idea? The idea is that even the sun, even the desert, has some microscopic organism like cyanobacteria, algae, fungi, different type of bacteria. They are living there, but they are not dead, but they need a triggering in order to growing up and produce and changing the characteristics. Okay, so imagine that they found bacteria at the age, with the age of 2.6 billion years. They took, let's say, some sun, they did the analysis, they found this small microscopic organism inside. So what is the idea? The idea is that they start planting, they start growing, cultivating this biocrust, but this inside the greenhouses, and that's all. So if you try to cultivate it in a controlled environment and in different scales, starting from the greenhouse and moving in drone, in fixed wing drone, in airplanes and in satellites, and see how the big surfaces are changing, the reflectivity, the fertility will change. So this is the idea. How? By, for example, I designed this country system with some sensors. So the sensors were there. The idea was to apply EM and geoelectrical and to have also some cameras to get the differences. This is the net of electrodes that they were able to see in the root zone how this biocrust is growing up. Then, like the grass, there are some people that they grow the grass and then just putting the grass in the park and they just let them grow by itself. Okay, so this was in general the idea. This is part of geophysics. I didn't apply because this was submitted in 2017. I got the results for the second, so it's not failed, it's not rejected, but it was passing the second evaluation. But I got the offer from KVPM, so I moved to Saudi Arabia. So I didn't have the chance to apply this. So everyone is welcome to, I can give him the final, all the proposal in order to materialize it. So the final remarks, I would like to close and then to move to the other requested by your association information. So I would like just to close saying that it's very important to apply different geophysical methods in combination with other methods, other disciplines. We need the chemistry, we need the civil engineers, we need the environmental engineers, we need the geologists, we need the petroleum engineers, mineral engineers, in order to be able to design, to protect the environment, to explore the natural resources, to monitor the environment, and of course, to adapt the climate changes within the area, the living area. So this was actually all my talk. So it's 42 minutes from the beginning. I hope it's on my time. So I will continue now, just giving you some information about the mineral exploration, the current situation in Saudi. So the biggest company about, maybe the only company in Saudi about the mineral exploration is the Ma'aden. Okay, so this is from the original website, the official website. And on the left side, you can see the exploration part. They are doing some gold and base metals. They extract phosphorus from phosphates and fertilizers, some industrial minerals and some aluminum. So I have, let's say I concluded everything in order to make your life easier. So you can see concerning the gold, they have the Ma'aden Gold and Base Metal Company, the MGMBM, and the Ma'aden Barrick Copper Company. So they are extracting, they have some mines for gold, copper, silver, and zinc. As you can see here, they have 6 gold mines. This is the second part about phosphates. So they have the phosphate company, MPC. So the idea is to to extract the phosphorus. At the same time, they have also some other industrial minerals like bauxites, kaolin, magnesites, and magnesite products. This is the aluminum, the last part of the Ma'aden. So it's the most important is that Ma'aden established a joint venture with Alcoa. Alcoa is the world's 3rd largest aluminum producer in the world. And they invest a lot of money in order to build a huge factory in Saudi Arabia. Why? Because they have the energy. Why they have energy? Because they have the oil. And since they don't care about the power electricity, it was very easy to build there. And there is plenty of time, plenty of space. The only problem is the water. They have a problem with water. So they built a huge pipeline in order to transfer the water from the coastline, desalined water from the coastline to the inner part of the Saudi Arabia. And of course, the Ma'aden Bauxite and Alumina Company, the BAC, that is has all they have the mines, they have the crushing, they have also the handling facilities. So can I continue? It's 45 minutes. Can I continue with the college, presentation of the college?
Yes, sir. Please go ahead.
Okay, thank you so much. So I'm going to present you our college. The college is the CPG, is the College of Petroleum Engineering and Geoscience. If you ask me, after 20 years in academia, is the best place that someone can go and have interaction with industry. Is really the best place for university-industry collaboration. Why? Because we are here. This is the KFUPM campus. This is Saudi Aramco. This is the campus of the Saudi Aramco, the headquarters of the Saudi Aramco. Saudi Aramco is the biggest oil company in the world. We have the KFUPM Business Park that we have several companies. This is the US Consulate. We have the Dagran Techno Valley, which is this area, which is next to the university. Actually, we have also our own building within the DTV. And in this Dagran Techno Valley, there are companies like Weatherford, Argas, Halliburton, Honeywell, Sipchem, Baker Hughes, General Electric, Schlumberger, Rosen, Amiant. So you can see there are many, many different companies. Now also Sabic with petrochemicals that belongs to Aramco is going to move inside the Dagran Techno Valley. Why? Because we would like to give to the students the theory, then from the theory to have the internship for the practices, then from the practice move to the application, and the last part is the commercialization, because everything we want is to move, let's say, from A to Z, not just idea, but to materialize the idea. And this is one of the reasons that we have petroleum engineering this is based on QS 2021, but last week they announced the new position. So the petroleum engineering department is the 7th in the world, and the mineral and mining is 16th in the world, and our university is the 4th in the world in US patents. Okay, so you can understand that it's very, very important to move from theory, as I said before, from theory to the final product. And CPG is 3 different identities. We have the Petroleum Engineering Department, we have the Geoscience Department with Geology, Geophysics, and Environment, and we have the CIPR. So CIPR is a Center of Integrated Petroleum Research. So I'm also the acting leader, program leader in geophysics in CIPR. So we have very good students, they are happy. We participated in different, let's say, competition. We got the first position, the gold medal in AAPG, the second position in Petrobol 2020 last October. And how actually they decided, the rectorate decided to do that. And of course, you can understand that it's because of the money. They have the money, and for that reason, they are able to attract very known university. So now they have global leadership with Stanford, with Edinburgh University, with MIT, with Cornell, with Heriot-Watt University. So we have every month meeting with committee from this university in joint programs. We send our students there. They are coming, their students are coming here. We have very active collaboration. We have joint PhDs, we have joint MScs. So everything, it works good. So what is missing? The students, because we have only few students. And I'm really happy that I'm able to talk to you because I know that your students are excellent, are more than excellent. It's the best student that someone can find in the market, I mean, in academia. We have also some other buildings. So this is the new building, the 78, with all the research facilities inside. This is a 78. This is the building that we have inside DTV. So that is some of the places. We have different laboratories, and very recently, this is the beach that belongs to the university. We are building one shallow well facility. Shallow well facility means that we have 5 boreholes of 500 meters deep, and we will install in there different geophysical sensors in order to apply cross-well EM, cross-well DC, cross-well seismic tomography, vertical seismic profiling to get some well loggings. And at the same time, we have a pad here with different targets, and we'll be able to apply with our students measurements for educational purposes mainly, but also someone can use it for research in order to get the magnetic and the gravity response based on the buried anomaly. So this is what we expect to have. So this is the building area. Should be, looks like this. So this is the research facility. I need 2 minutes more. This is a different facility. The CIPR, the Center of Integrated Petroleum Research, is one cycle. We have the multi-scale rock analysis, and we have the colloids, the oil field chemistry, the geophysics, and the rock physics. We have different instruments. I will go very fast just to show you some of the instruments that we have in order to do all the different analysis. I will share you this presentation with you, and will be available for the students also. Different types of scanners in order to get the samples and do analysis, 3D monitoring, microfluids, like this MRI, and so on. So I think I finished. Just give me 1 second. AOR is the enhanced oil recovery. Okay, thank you so much. I hope I didn't waste your time. It's 51 minutes after the beginning. Thank you so much.
Thank you.
Thank you, sir. I think we're very grateful to you. Yeah, next program, sir. Dr. Panigrai, please.
Yeah.
I think you invite Madam.
Sure. Thank you, Professor Pantelis, for giving a wonderful presentation, plus the facilities which are available with you at Saudi Arabia in your university. Now, we have a few questions, and may I request Professor Madhumita Das kindly place these questions as a moderator to Professor Pantelis. Professor Madhumita Das, please.
Okay. A very good evening.
Thank you, madam.
Sorry, you have to unmute, Madhumita. You are muted again. Yes. No.
Is it okay now?
Yes, now it's
Yes.
okay.
Yes.
Yes. Now you're absolutely.
Okay. So, a very good evening to all of you. Actually, thank you for Dr. Pantelis. It's a very good presentation. And the most interesting part of your presentation, which I liked, is you have quoted one sentence that geologists don't believe the geophysicists. Very, very interesting comment. And now I would request you, we have couple of questions for you. The first question is from Dr. Subhas. Which one is best method for groundwater exploration in hard rock?
Yeah. So it's there are different methods. For example, if the sediments, or if you have the hard rock, so you have a fracture aquifer. Okay, so you expect the fracture aquifer, the aquifer to host it inside the fracture. So if, for example, the top layer, the sediments are only a few meters, then the best methods is, and the fastest and the cheapest method is to apply VLF. So using VLF, you can get information about the geometry, and now there are also software in order to invert the data and produce 2D sections from the VLF data. So you can get the geometry of the fracture zones, and you can get also some information about the slope and so on. If you have time, if you have the instrument, if you have the money to go and get some more, I would like to get some more geophysical measurements using DC, which means geoelectrical measurements, especially 2D or 3D geoelectrical measurements. This will be much easier to match the conductivity change based on that found from the DC measurements with the VLF, the electromagnetic measurements. Now I can also suggest the TM, the transient TM in case, but all has to do with the depth of the groundwater, the features, the fractures, the width, the thickness of the fracture zones, and of course the thickness of the top layer. So it's electrical and electromagnetic is the best methods in order to find the groundwater in hard rocks. This is my answer.
Thank you, thank you. I think Dr. Subhas, you have got it. Electrical method is suggesting the best method for groundwater exploration. The next question is from Dr. J.V. Ramarao. Have you been using GPR techniques for near surface applications?
Yes.
GPR techniques for near surface applications.
Yes, several times. I mean, you know that the GPR is the highest accuracy and the highest resolution methods for near surface. We have 3 different systems. We have the 100 Hertz, 400 Hertz, and we have also the 35 Hertz, which is goes down to almost 50 to 60 meters. And next Saturday, I'm going to collect some data in one area that we have some uplift. So we have some diapanism in a small scale that we are going to apply 3D GPR. And 3D GPR means that you will collect parallel lines and you collect also perpendicular lines in order to have the cross point to produce the 3D volume. We have the GSSI system, so we use usually the Radan software for processing and for doing also the 3D processing. So yes, we are using it's really known and it's a very, very good method, especially for utilities and shallow applications.
The second question from Dr. Subhas is, which geophysical method is best for seepage study? Seepage.
Yes. Yeah, so it's we had one survey, 3 surveys in dams. So dam in the main dam body, you need to know if you have any seepage. You need to be able to monitor the seepages. If they are, for example, it's really fast. If you have problems, probably with the failure of the main body. So there are different methods. Usually we apply geoelectrical methods, something that is very cheap, very good, and very, let's say, promising based on the new methods, new processing methods is self-potential. So in self-potential, you can get the movement of the fluids within the main body. within the dam body, so you can get an idea. You can inverting the data, and this is my colleague Payal Rani is doing through the 2D interpretation, can find the sources, the geometric characteristics of the sources. So the geometric characteristics of these areas that they are using as the pathways for the seawater, for the water to move within the porous material. And then you can apply GPR, you can apply geoelectrical resistive tomography, but for starting, something that is very cheap is self-potential.
Okay. Now Professor Debashish Sengupta from IIT Kharagpur, he wants to ask a question. I would request him to ask the question in the question answer box. Professor Sengupta, please put your question. If you are there, we will wait for his question. Now,
do you want me in between to answer, because I don't know if you can see my screen. I have all the questions here. Do you want me to answer one by one? Very fast.
Yes,
So in olive oil production, we have some ways that they are N-NAPL. They are not D-NAPL, denser. So they were floating, so they're on the top. So yes, we can see the D-NAPL. We applied several methods. We found them with using the DC, using not the GPR with the different antennas. So it's the... Yes, please.
I think Mr. Panigrahi and others, can you please keep quiet when Professor Soupios is answering? So if you want to discuss over the telephone, please discuss.
Okay, yeah. I'm continuing. Okay, don't worry, no worry. So it's there are different methods in order to find D-NAPL or N-NAPL. So it's we have also our own software in collaboration with the university, the Western University in Canada, the old university they called Western University of Ontario. And so we were able to find and monitor and simulate how the fluids, the NAPL fluids are moving within the grain material. So we have the joint inversion of petrophysical and geophysical images, geoelectrical geophysical images. Does hydrofracking for shale gas cause seismicity? Yes, you can get some seismicity. You can apply some micro seismicity, and you can do also some moment tensor inversion in order to define the fracture zones and the characteristics of the fracture zones. This is also very important because if you find the fracture zones, then you can find which is the prominent fracture zone. You can find how these fracture zones are growing. Okay, so this is really important. This is something new because they have completely different behavior, the shale gas. And we are working on this. We have a network of 30 low frequency standalone seismometers that are connected to one system. This belongs to GTEC. And we have also the software for processing. My question are interesting here. Geoscientists evolution of Arabian desert, landscape evolution, geoscientific evolution of Arabian desert. You know, it's very important nowadays. We have one master student from Berkeley University of California, and what he's doing, they are working, you know that the easiest part to make an analog with Mars and the moon is the desert. So if you go and actually Ruba Khalid empty quarter desert can produce sand dunes that they have exactly the same shape, like the shape of the dunes that they found in Mars. So they try now to do some surveys based on the environmental characteristics, how the sand dunes in Saudi are changing, and we are doing some measurements with LiDAR, with GPR, with TM, and we're trying to understand how these sand dunes are changing and to predict, to apply some like figure printing backward in time to understand the behavior of the sand dunes in Mars. Okay, so this is about the evolution, compacting classification with increased human intervention by using GPR. Yes, we applied GPR. Actually, we applied when I was in New Jersey, in in the eastern coast of US, in Rutgers University. We applied several times GPR for CSI, for crime to help the police. Okay, so if the soil is, what is the idea? The idea is if the soil is undisturbed, then you will get a homogeneous response. If the soil is disturbed in one area that the police probably believe that something happened, then you can very easily find it with GPR. So if I understood well about human intervention, so you can apply GPR. GPR is one of the methods that usually applied with DC, with electroresistive tomography for human intervention. Does shale gas extraction lead to hydrofracking? More or less, yes. I'm not an expert. We have some petroleum engineers, expert in hydrofracking. So I can give you the email. You can contact them. We can have a meeting all together. So it will be a great idea to start working all together. Do Saudi Arabia use nuclear power for desalination? Not yet. The first nuclear plant in Saudi Arabia was actually we were part of the members of the company that was trying to locate the best places for the first nuclear plant in Saudi Arabia. The idea is to have in the eastern part of Saudi Arabia a nuclear power plant, and they're trying to find a place with the lowest seismicity next to the coastline and to avoid different problems that can probably rise because we have some knowledge of what will happen. So there is a plan for nuclear plants in Saudi Arabia. We don't have any nuclear plants, but I suppose this is also part of the Vision 2030 from the Prince. I suppose I answered all the questions.
Is it possible to ask some questions?
Please.
Oh, yes.
With your permission, Professor Madhumita.
Yes, please, sir.
I have two questions, Professor Pantelis. The first one pertains to your SIP technique for the arsenic, part.
Arsenic removal, yes.
Both in Bangladesh and in many parts of eastern India, in particular in West Bengal, in the eastern part of India, and we suspect northern part of Orissa, which is contiguous with Bengal, arsenic is a serious problem. I was quite surprised that your SIP technique, because you had used this date palm biochar, you said, in many parts in Bangladesh, the Dutch technique of taking the arsenic water, spraying it so that the arsenic oxide that you form, that actually precipitates, goes through the sand, gets filtered out. So that's one of the techniques which is used, and we tried to use it also in some parts of West Bengal. So I was trying to find out, your date palm, it goes through a chemical reaction or basically doing a physical kind of filtration?
Yeah, I can show you here one result because we modified it with iron. So this was the idea. I don't know if I have the presentation. No, I will just explain you. So we tried different types of temperature during the pyrolysis in order to produce the biochar. And then we found that the absorption was, the decrease of the concentration of arsenic was around 40 to 50%. And this was also in agreement with the bibliography. Then we found the bibliography that we can enhance the absorption rate by adding some iron. Okay, so with some iron, so the biochar that we finally used for the absorption process, for the removal process, it was with iron at 500%. It was not the same successful, the iron biochar at 800 degrees of Celsius. So then we mixed with sun and we just have these columns, get the water sample contaminated with 5% of arsenic, because we would like to see also the threshold of monitoring. If we were able to see 1% of arsenic, 2% of arsenic, 3% of arsenic.
Like the percent that you are talking about, Professor, the percent that you are talking about, we are actually PPB level. So
yes, PPB level.
Yes, the PPB level. Is your SIP sensitive to 1 ppb, 2 ppb kind of changes?
Yes.
Points, because Otherwise, you need a very costly equipment. In many parts in the world, the poorer countries, they'll find it difficult even to determine the amount of the arsenic. So how is your SIP?
The SIP was able, this was a 3-month study. So this was just the beginning. So it showed 1% and 2% is we were able to find the arsenic and see the removal. So what is the idea? If we build, let's say, one filter that is filled with this biochar, this carbon organic materials. So someone should understand what is the saturation of this material. If the material is really saturated, that means that you have to refill it, you have to regenerate it, you have to change it, then you have to do it. Otherwise, the water comes inside contaminated, it's continue like that. Am I right? So the idea of SIP was to apply it as monitoring, because we inject some current battery and we measure the potential difference in the other, again with one multimeter.
But your arsenic was occurring in the aquifers deep down as a geological accumulation of arsenic, or was it somewhere occurring at the higher levels?
We collect data from the
aquifers.
From the aquifers. They sent us the data from Pakistan, because the student was from Pakistan, and they sent us some table from there to do the analysis.
And my second question, the last question is pertaining to the GPR. In India, in various places, GPRs have been used. I think one of the most elegant has been the subterranean river, where 3 rivers in India, they meet. The third river is never seen. So a French professor has actually used this for 10 years in finding out the course of a river. And in our province of Orissa, where the Sun Temple of Konarak is established or was erected, there was a river which was subterranean, and people have used GPR very successfully now in finding out the course of the river, which is deep inside. So that's one of the things going on in Odisha now, not completed as yet, the GPR studies. So where we are interested in finding out GPR in some archaeological excavations also, finding out whether there are actually iron ore slags underneath the ground, and you don't have to figure out everything, but with GPR, whether you would be able to find out. So that was our interest. I think I'm done with that. I'm done with my questions, Professor Das.
So you're asking me if you can use the GPR for geological prospection. Am I right?
Yes.
Yes, you can, and you can get really very good results. I'm going to just I will spend less than 1 minute for your time. I would like to show you.
No, take your time.
It's, because it's very nice. I have a very nice presentation about the measurements that someone can apply in urban environment to define. Here, for example, I will show you what I mean. So here is GPR. So this is one place. Actually, it's one place in Rethymno. This is one school. So it's a yard from one school. I will make it larger in order to see. So it's in the presentation view. So you can see the yard. Come on, it's coming. So this is the yard, and we decided to design one geoelectrical and GPR survey. So first of all, because it was everything covered by asphalt, we had to open some holes and put the electrodes in order to apply the full 3D DC survey. And we get on the right side, we can see the GPR system. So this is all the lines. This is the buildings that we had in between. You can see with 3D resistivity model, it seems that after the depth of 35 centimeters, you can see here on the top, the depth slices, 35 centimeters, 35 to 75, 75 to 122. You can find some linear structures here and here, like rooms, but you cannot really understand what is it. So if you go to GPR, so this is a GPR images. You can see very beautiful images for the different depths, 90 centimeter, 100 centimeter, 110, 120. You can see these roads. You can see here the structure. And after that, the archaeologists decided, so this is the total maximum depth of 200 centimeters, so it's 2 meters. Okay, and this is more than enough for the archaeologists. They don't want to dig deeper. So This was the final schedule based on the GPR. So this is the linear features that they found based on filtering of the GPR data. This is the linear feature found based on the filtering and the processing of the signal processing of the DC data. This is a combined DC and GPR, and this is the excavation. You can see that they found very beautiful structures. They just confirmed the results, especially from the GPR. So it's very easy to use the GPR and get very detailed results.
Where do you find a great divergence between your electrical resistivity data and the GPR data? Have there been cases where you have found it very difficult to reconcile these two data?
Yes, yeah. For example, I will show you here. We applied here on the this is a bus station that I showed you before, the case with the area that we would like to develop. We had the GPR system. We had also the ERP, the DC, the ERT, the electrical resistivity tomography.
Yes,
you can
yes.
see the touristic area, many people were walking, the bus come in and out, so it was very difficult. Most of the measurement they collect during the night. I will show you now the results. This is the GPR, and the GPR show actually nothing. Sorry. Yeah, so
Okay.
don't really, it's just noise. Why? Because we realized that below the surface, it was the net of iron bars. So these was many scatterers that really distort the signal. And we got results only from the ERT that show some tunnels that they were responsible. So yes, sometimes you don't have agreement, but you have to test different methods.
Thank you. Thank you. I get your point.
Sir, can you go to the Dr. Panigrai, sir?
Yes.
Dr. Panigrai, thank you.
I think we are beyond the time schedule. Just I will have a quick answer from Dr. Pantelis.
Yeah, very quick.
This is the last question from Professor Debashish Sengupta from IIT Kharagpur. Did you see any NaPl from the olive oil production? NaPl from olive oil production.
Yes.
Have you come across that?
Yeah, we have published 2 papers that show how to apply the NaPl monitoring using DC methods. And whoever is interested, I can send him. So he can send me the email. I can just reply, send him the papers. Yes, we have the way. We have also the software.
Okay.
Okay. And Sir, President Sir, Omkar Manti Sir, last question.
Not me.
There is another question from Dr. Sudesh.
Madam, I think
okay,
we are
take one
exceeding
question.
the time.
Take one question.
So please, last question. You please go on. I think after that one,
Dr. Mahapatra.
Sir.
Now allow Professor Madhumita Das to cover the last question. Where is it from? Which place?
Only. It's just there are 2 questions, but I am combining it.
Yes.
But the question is from Dr. Sudesh Kumar.
Okay.
Combating desertification with increased human intervention. So, how do you use GPR survey? How do you use GPR survey to combat desertification?
Yes, I have already answered.
Desertification.
Yeah, I have already answered this question. I mean, using GPR, you can find the if the soil column is disturbed, you can get the signal. You can get an anomaly with GPR. So if you go in a place, and this is something that we applied, especially in US, they are using the GPR system for crime scene investigations. Okay, so this is a way. I mean, they are trying to see if the soil is disturbed. If it's disturbed, something illegal happened. So this is the human intervention. So you can also measure the permeability, because if, for example, you apply some pressure to the soil, the permeability is changing, the fluids within the permeability, so the porosity is reduced, and you can get also some signal again with the GPR system.
Thank you. Dr. Panigrai.
Yes.
Thank you.
So we have come to the end of the session, and it's my proud privilege to propose a vote of thanks. We are extremely honored, Professor Pantelis, for your absorbing presentation, in which we also had a quality audience. Your presentation was very informative. Particularly, we never knew about the application of urban engineering geophysics for urban planning, and some of the data which you have given is quite interesting. 60% of the population of the world will be in cities by 2025. So therefore, there are seismic risks, groundwater contamination, the degradation of environment, and like many other aspects which you have covered. And also after this, we had a wonderful question and answer session, which was moderated by Madam Madhumita Das. In fact, this is the first time we are having a presentation from international speaker live. And thanks to the technology and this platform which we are using, which we never thought about 2-3 decades back. Now it is in reality, and we are extremely thankful to you, sir, Professor Pantelis, and also I'm extremely honored to thank our president that he has been so much of pain to see that we have this program as a wonderful success. And I also thank our committee members who have taken all these pains to find out how we'll be able to, how the society will be benefited. Last but not the least, the students and all participants and my colleagues from SGAT who have been in this entire program for its observance, and a very good night to all of you.
Before we hang up,
okay, anything?
Before
Yes.
we finish, I have a special request to Professor Pantelis and our General Secretary ought to have said that we would request Professor Pantelis Soupios to be the first international member of our Society of Geologists and Allied Technology.
It will be my pleasure.
We'll invite you to be a member.
Thank you so much.
We hope you'll agree.
Yeah, of course I agree.
Okay, thank you very much for accepting the request of our president to become a member, international member. And with this,
no, there is another request by Professor Madhumita Das last night, and
yes.
I hope you remember that.
Yeah, the pages. Yeah,
before the end of the month, you will send.
I remember everything, Professor.
Yeah. That's right.
You'll send the presentation report to our bulletin. Thank you very much. You are a part of us now.
I have selective memory. If I something I don't want to remember, I just discard it. I remember that. Don't worry. I would like to thank
you very much.
I would like to thank especially.
Thank you very much, everybody,
and
good night to all of you.
And thank you all for everything.
Thank you. Thank you very much.